to you, Najwali.
Thank you, Kamalika. Now, first of all, welcome back to the last session of first symposium of cellular automata technology. I hope this session is also enrich our knowledge about cellular automata technology as previous sessions. And in this session, we're glad to introduce Professor Debdeep Mukhopadhyay from the Department of Computer Science and Engineering, IIT Kharagpur. However, he may need not any introductions, but we take this privilege to share some of his achievement, like he received the National Science Academy Young Scientist Award and National Academy of Engineering Young Engineering Award, that is in the 2010, Associate for the Indian Academy of Science in 2012. Swarna Jyoti Award, he received the Swarna Jyoti Award from 2015 and 2016. And most important, that is the highest science award that he received at 2021 Shanti Sarup Bhatnagar Award. Apart from that, he also received that Khosla National Award in the 2021. And his research interests are hardware security, cryptography, design automation of crypto system, and cellular automata. So in this session, we'll enrich our knowledge with a topic revisiting logic obfuscation using the cellular automata. Over to you, sir.
Okay. Thank you, Professor Nashkar, for this kind introduction, and also to all the organizers, Professor Das, Professor Bhattacharya, and all the organizers of this event. Thanks to all of you also for assembling to hear this talk. And so this talk essentially will be on, I would say, an intersection of on cellular automata, of course, which is the primary objective of this workshop, and a topic on hardware security, which is called as logic obfuscation. So I will try to kind of bring in the first of all, define the problem of logic obfuscation as is often discussed in the domain of hardware security. And then I shall talk about a possible solution using cellular automata, some of the pros and cons that we encountered in this direction. So first of all, I would like to mention about my collaborators, Akashdeep Saha, who is my current PhD student in our department, Hrivu Banerjee, who is an UG student from the Department of ETC IAST Shibpur, and he was interning with us during this some of these works. And my colleague, Dr. Rajat Subhra Chakraborty, who essentially is also a colleague of mine. So with this background, so let me try to kind of first of all define the problem of so we know that our integrated circuit industry is growing, and it has become extremely enormous, and because of the growing size or the magnitude of the design cycle, which essentially starts from the RTL code conception to the gate level design to the point that you essentially go into the final GDS2, which is essentially used to fabricate the device, and finally the testing, packaging, and eventually the sales, unless we get the IC or the integrated circuit in the market. So very often the IC designs are outsourced to foreign fabrication laboratories, and this raises the question of trust. So the idea is that as an adversary, or from the adversarial point of view, there are many entities, in particular the manufacturing, testing, and packaging, which are done at sites which are unknown to us. And therefore, this raises the questions about or concerns about the unauthorized overproduction, the design counterfeiting and piracy, and of course, hardware Trojan insertions. So all these things essentially kind of raise several alarms in our, and I would say lack of trust on the hardware that we procured and we utilize for critical applications. So as you can understand that, like the problem of overproduction means that you are essentially, like stealing the IP of the designers because you are overproducing them without paying them the appropriate revenue. And likewise, the problem of counterfeiting and piracy also leads to, like the leakage of the IP and directly conflicts with the intellectual property of the designers. The problem of hardware trojans is even more, I would say, subtle and devastating, because it means that there are small modifications that can be done inside the chip, which are very difficult to detect by our standard testing methodologies. But at the same time, they can be triggered at appropriate conditions and by appropriate input vectors, which can lead to the total collapse of the overall security. So this ensures us, or like this motivates the hardware designers to look into a solution which are called as logic locking. So the idea of logic locking means that when you essentially fabricate the chip, then there is an inherent encryption that is done on the netlist. Okay, so that means, right, the objective of logic locking is to obscure the functionality of the original IC design, and you do that by inserting some additional gates into your design. As you can see probably in this illustration over here, this shows a circuit diagram that has been taken from a very standard benchmark. And while this circuit has got certain primary inputs and also certain you also introduce some additional gates shown here by these two gates, which are, one of them is an XOR and the other one is an XNOR. And these two gates receives an input or an additional input, which are essentially the key inputs. And these are what we call as the key gates. So the idea is that if you apply the correct configuration to this, or correct input sequences to these two keys like K1 and K2, then the chip should function as the normal chip. Else or otherwise, like when you are entering a wrong key, then the chip should essentially function in a completely arbitrary manner, in a different manner from what is expected. And therefore, it becomes extremely hard for the adversary, without the knowledge of the key, to know what is the real circuit. Okay, and it is really difficult for the for even the person who has access to the netlist and also the internal details of the chip, because the key essentially is unknown to the adversary. So therefore, so now the question is like, for example, in this circuit, you can see that the correct key is 0 and 1. That means if you feed in a 0, and like for K1, if you feed a value of 0, and for K2, if you feed a value of 1, then these two like gates will become transparent, and therefore the circuit will work as per the original specifications. So very often these keys are stored inside the chip in a non-volatile memory, or it can also be externally applied. Okay, and the idea is that this essentially becomes the root of trust of the chip against all the previous threats that I mentioned, like IC piracy, counterfeiting, as well as this also becomes or makes it more difficult to insert trojans into the netlist or the circuit. So this was a famous paper that was published way back in 2008 by a group led by Koshenfar, and showed that like you can essentially involve such kind of logic blocking techniques to really ensure or increase the trust on our IC circuits. Now there are different classes of like logic blocking techniques. So as the two important categories are what are called as combinational logic locking and sequential logic locking. However, there has been a very interesting follow-up work in 2015 by the very talented Professor Subramaniam, who showed that this can be thwarted by what are called as SAT attacks, or satisfiability attacks. So this was a breakthrough attack which actually broke all the existing combinatorial logic techniques which were proposed at that time. And the technique of breaking these solutions were based on the capability of solving certain Boolean satisfiability problem, and actually framing the problem as a Boolean satisfiability problem, and then using state-of-the-art SAT solvers to ensure and obtain the secret key. So in this case, the threat model is as follows. The adversary is given a locked netlist. So when I say a locked netlist, it would mean that it has got the netlist, but it doesn't have knowledge about the secret key. The attacker also has got an access to an oracle. That means like a chip that it probably has an access and to an activated chip. That means for which the correct key is configured, and the adversary can feed in the correct input and also obtain the corresponding correct outputs. So now the objective of the adversary is from this, two things like the locked netlist and the activated chip access, which we called as the oracle access. Can the adversary obtain the value of the keys or the keying elements? So in this attack, what it does is it tries to kind of transform the locked netlist into a CNF form, okay, and that is and uses them to obtain the key. So the basic crux of this attack is based on the definition of what is called as distinguishing input patterns. So also abbreviated as DIP. So DIP would mean that these are input patterns. So suppose like if you take two keys, like say suppose there is a key, suppose like you take a possible key, say because there suppose you have got say you feed these two keys to this circuit, to this netlist, and you obtain. So when I say to the netlist, it means the locked netlist. And suppose you obtain different outputs for these different key assignments. So that means that one of these keys is definitely wrong because you are getting two different outputs on these two keys. Now what you do is you check whether whether these at least one of these keys, I mean the outputs corresponding to one of these key values corresponds to the output that you get from your oracle access. That means the activated chip. And if you find out that none of them matches with your oracle or activated chip, then definitely both of these keys are to be discarded, which is the best possible case. However, if one of them matches and the other one doesn't match, then you can definitely discard the one that does not match. But the one that matches, you include that as a clause in your CNF formulation. So that way you keep on adding constraints and gradually, and you keep on trying to solve them by the best possible SAT solver that you have. Eventually it turns out that after a certain amount of efforts, you will not be finding out these kind of key pairs or distinguishing input patterns, and that ensures that all the remaining keys that stay at that after that pruning process are possible candidate keys. Now it may be emphasized here that the activated chip most often doesn't get activated only in one possible key configuration, but maybe a small subset of the possible key configurations, and therefore all the remaining keys become valid keys. So this is a very strong attack, and it turns out that if you implement them, like for example this is an in-house implementation using Pramod's tool, we find out that the correct key, and this is done on the circuit that I just now showed in the previous slide, and you can see, of course it's a very small circuit, but you can see that it indeed obtains the key which is 0, 1. Okay, so therefore, right, how do you really protect against SAT attacks has been largely what the designers from 2015 onwards started to do, and there were different kinds of proposals which essentially emerged. Like some of them are abbreviated here, some of the important ones: SARLock, anti-SAT, SFLL, and CASLock. Okay, so all these things essentially, interestingly, they are essentially what are called as one-point functions. So one-point functions means that they have a very low output corruptibility. That means if you give a wrong key, then you will probably find that there will be one out of maybe 2 to the power of n, if n is the number of primary inputs, possible cases where there will be a wrong output that is generated, whereas for the rest of the cases they are the same as your oracle circuit. So that immediately means that they are difficult to detect, because if you are using a SAT based technique to get them, then your SAT will be pushed into the brute force complexity, because there is only one out of the possible 2 to the power of n, if n is your key length, okay, and which essentially malfunctions, and therefore the SAT is kind of like constricted to find out that one out of an exponential possibilities, and therefore it may end up in running like for exponential amount of time. So this really helps to protect against SAT attacks, but they will suffer against other forms of attacks, which probably may be even more easy to mount. For example, you can simply bypass them. You can probably apply or employ something which is called as a removal attack, and that basically means that you do a netlist analysis and you just understand where are your XOR sites, and you just kind of remove them from the circuit. Okay, and likewise, right, remember that you have access to the netlist, right, and therefore you can do such kind of operations. Likewise, you can do a function analysis to identify the XOR sites, and you can eliminate them from your circuit. So therefore, right, I mean, the idea of while these were not like the best possible designs to prevent SAT attacks because of these aforementioned attack vectors, there was another line of research which tries to develop what are called as SAT hard instances. So there are examples of them are called as full lock, interlock, and another one that we published at DAC called as loafer. So all these things essentially are really like if you apply SAT based attacks, it turns out that they are difficult and it takes exponential or at least a large amount of time to solve, and for reasonable amount of circuits or key lengths, they are not amenable to SAT based attacks. But at the same time, they also suffer from the problem of high overheads, and one of the objectives of developing these logic locking techniques is to reduce the overhead of your implementations. And this essentially brings out to a solution that was proposed in DAC in 2019 using Cellular Automata. So I will not introduce, of course, what is CA to this audience, but I will just quickly mention that one of the reasons why CA essentially turns out to be very promising in this context is because of its regular structure. And that essentially, of course, is more amenable to VLSI design. So in particular, this solution tries to look at one special form of cellular automata, which essentially falls under the category of non-group additive cellular automata. So this cellular automata is what is called as a D1 star CA, and it is, and as we know that it can be configured by a rule vector which is like 90, 102, and so on. So 90, right, I mean, just for completeness, is basically nothing but a CA which has got which depends upon the left and the right cells, and the 102 essentially is a rule which indicates that it depends upon the self and the right. So if you kind of configure your CA using these rule configurations, then this is the state transition that you obtain. So this is a small example of a null boundary 4-cell D1 star CA, and you can observe that it has got some reachable states and some unreachable states, and it follows a nice like organization of the state spaces. So likewise, there are like different variants of the D1 star CA, which are called as the D1 star CA dual, where you change the first rule vector from 90 to 165. So 165 is nothing but the rule where you do an XNOR on the left and the right cells. And likewise, if you take the D1 star CA dual B, you make a change on the third cell where you make it 153, where 153 is nothing but the XNOR of the self and the right cells. So if you take this, right, the interesting part is you see that what was reachable in the previous case essentially becomes like the reachable states in the next configuration and so on. So this logic locking mechanism, which was proposed in DAC in 2019, uses these three automata and tries to develop a scheme. So let us before I go into the scheme, let us take a quick look at some of the properties that essentially were established in prior work. And like I will just quickly mention about some of the important properties. So first of all, if I take the D1 star CA, then all the reachable states are cyclic states, and in particular, the cyclic states are are essentially those which comprises of the even number of the states with even number of ones. That means they are even weighted states. And this you can observe. If you observe this, for example, you can see that all these cyclic states have got even weights. So likewise, if you can prove that if your cells range from like 2 to the power of minus k minus 1 plus 2 to the power of k plus 1, then there is a maximum transition cycle length of m equal to 2 power of k. In our example, this k is 2, and therefore you get a maximum cycle length of m equal to 4, which you can observe from here. Likewise, if 4 is the or m is the maximum transition cycle length in the state transition diagram for an n cell d1 star Ca, then the set of transition cycle lengths that are essentially over there essentially are nothing but the factors of m, and that's why you get cycle lengths of 2, 1, which are essentially the factors of 4. So finally, there is a property which says that if the machine makes m or any multiple of m number of like d1 stars mode transitions from a reachable state, then it will return back to the original state. So that is pretty obvious from the state transition graph that we just now saw. So now how does the CA-based obfuscation work? So in order to obfuscate the finite state machine transitions, the designers propose this, that is, you use two variants of key. So one is what is called as a C key, or like C like C or cellular automata gets configured as a D1 star CA, whereas if the CK is equal to 1, then it gets configured as D1 star CA dual B, where you just change the third cell from the rule of the third cell. And in order to obtain or obfuscate the transitions, you use the output of a special logic which is called as the interrupt logic. Also, we will use it or abbreviate it as or denote it as IV or interrupt vector. The idea essentially is pretty simple. What you do is that if you want to make a transition from SI to SK, so imagine that the encoding of SI is, say, suppose FI, and the encoding of SK is FK. And if you make, if you set your cellular automata, like to this state SI, and if you make a transition, and suppose it makes a transition to the state SJ, then you impose an interrupt vector which is equal to SJ XORed with SK. So therefore, when you apply your cellular automata, you get the state SJ, and when you XOR it with the IV, then the SJ and the SJ gets cancelled, and therefore the final state is SK, which is as per your FSM transition. So therefore, depending upon the fact that your CA is a D1 star CA or your D1 is a D1 star CA dual B, that means if your CK is 0 or your CK is 1, this is the corresponding IV that you need to set. So therefore, your IV essentially kind of like obfuscates the transformation and ensures that eventually, if you apply the correct key, then you should be able, then your IV should be able to kind of bring your state to the appropriate state as per your FSM transition. But if you give a wrong key, then you will be selecting a wrong IV, and therefore you will not get your state transition as per your finite state machine of your circuit. So with this idea, so this is essentially an illustration of how the configuration works. So you can see that there is this, like, so again, for just without loss of generality and for simplicity, we show a 4-state CA, but it can be also extended to larger dimensions. So if you take this encrypted logic here, and if you feed in the CK equal to 0, then you can see that this CK ensures that all the states are like configured to its correct state. But if you make it CK equal to 1, then you can observe here that it basically like makes an extra flip to the third cell, and therefore the CA gets configured as a D1 star CA mode dual B. Okay, and there is also another like bit that I would like to introduce here, which is called as C test. Okay, so therefore this is what I meant, that if you make the C test equal to 1, then the first cell gets changed and gets like inverted, and therefore this gets configured as a D1 star CA dual B dual A. Okay, whereas if you take your C test equal to 0 and you set your CK equal to 1, then the CA gets configured as D1 star CA dual B. So with this programmable function, or CA, you essentially can apply them to to work in your to make it work for your obfuscation. But in order to get this obfuscation, the designers use this property, which you can find in other prior work as well. So the idea over here is that you take your cellular automata, and this essentially is borrowed from the nice testability property of this CA, where if you start with SI, which is any random starting state which has got an even or odd number of ones, then if there are no faults or there are no error, then an autonomous mode or run of m+1 clock cycles, okay, in the like, say, let us say, like in the D1 start CA mode, and if it is followed by another autonomous mode run of the D1 start CA dual A, should return back to the original state. Okay, and this can be like observed by this example here, or is illustrated as an example here. So again, we take, without loss of generality, our 4th state example. So if you start with this 1101, which was like, if you just go back here to the original state transition, so it is one of these unreachable states. And from there, if you apply 5 transitions, which is essentially corresponding to your m+1 transitions, and then you follow it up by like 3 transitions, which is your m-1 transitions, then you get back to your starting state. And that way, you can do an error correction, and you have got better testability in spite of not having your scan chains. By the way, on the passing, I would like to mention that if your circuit consists of scan chains, and if you are talking about cryptography, then that's a bad choice, because people have shown that, or researchers have shown that scan can be exploited to perform attacks. And that way, this kind of structure of the CA essentially gives you nice testability, but at the same time, without the risk of having scan chains in your design. But then the question is, right, does it really ensure security? That is a problem that we would like to address in our talk. So in order to adapt this for like this obfuscation purpose, what the designers do is they essentially allow like they allow the transitions to happen, and they do not expose all the bits to the adversary. But what they do is they expose the MSB, or the maximum significant bit, to the adversary. So therefore, this is essentially denoted here by QSM+2. So remember that you first of all do these m+1 transitions, and at the end, the state that you reach is called as, suppose is, so this entire process, like starting from your initial state to the following m+1 states, and when you are exporting the MSB out of these states, this sequence is what we called as QSM+2. So therefore, in this example, if you take the first state, and if you apply 5 transitions, then you should get a vector of dimension 6 bits, because you are exporting the MSB for each state. So in this case, as you can see here, I start with 1101, I export a 1, I go to say all 4 ones, and I export a 1, and likewise I get a sequence which is called as QSM+2, and it is a sequence 111001. So the designers essentially like expose this to the adversary for the purpose of testability. And the idea being that if this is correct, then you essentially know that your design is working as per your specifications. However, the question is, right, I mean, does it really achieve obfuscation? Okay, so in order to like analyze this, we did this work which we published in IEEE TCAD in 2021, and we proposed a novel attack which we called as ORACALL. So this targets this CA-based obfuscation and finds out an interesting property. The first property is that if you allow, say, let us again take this 4-bit CA or D1 start CA and consider its evaluations. Okay, so you see that suppose this is your first evaluation with F, and then it goes to the state F1, then it goes to the state F2 according to the rules of D1 start CA. So if I start with F1, F2, F3, and F4, and if I apply the first rule, then the output of that is F2, F2 XOR F3. So remember, you are applying this 90102, and 102 is nothing but the rule which says that you take the self and you take the right and you XOR them. So if I take the self and I XOR it with F3, then I get F2 XOR with F3. And you export F1 because this is essentially leaked to the adversary. So you get F1. And if you get F1, then next time when you are leaking F2, you note F2. Okay, and in the third evolution, when you get F2 XOR with F3, that is obtained by by applying the next transition, then when you are leaking F2 XOR with F3, and since you have already leaked F2, it is trivial to get F3. And that way you can recover the entire initial state. So you can see that F1, F2, F3, and F4 can be recovered, which was the initial state cell of this transition. So therefore, even leaking the MSB is not a prudent choice when we are talking about obfuscation, because it leaks to the evolution of the initial state cell. So therefore, now let us get back to our original adversary model and see how we can exploit this property to perform an attack on the obfuscation. So again, let's quickly recollect about the adversary model. The adversary model says that the adversary has access to the lock netlist. That means the netlist which has got this extra locking gates with the unknown keys. And from the market, the adversary has also obtained an activated chip through which it can verify the correct input-output pairs. But it doesn't know the key, and the objective of the attacker is to know the key. So now the overall attack essentially is illustrated over here. So you see that we have got the initial mode, which is called as a test mode. So now when you are initially in your test mode, say I call it as S0, and if you apply you essentially can put the chip into the test mode, which means you can now apply this initial m+1 clock cycles to obtain this QS0m+2. And now the knowledge of QS0m+2, as we discussed, can be used to obtain the value of S0. So the adversary obtains the value of S0. So now what the adversary does is it puts the chip into the FSM mode and makes a transition of it from S0 to S1, and then again puts the chip back to the test mode and again obtains QS1m+2, which leaks the value of S1. So therefore, you are essentially obtaining the individual states through which your CA or your overall design is is making transitions. Okay. So now the question is, right, from S0 and S1, can the attacker obtain the value of C key, which is the key? So note that there are two possible ways in which it can make a transition from S0 to S1. It is either a D1 star CA or it is a D1 star CA dual B. That means it is either the CK equal to 0 or it is a CK equal to 1. So in both of these cases, the IV can be either IV1 or it can be IV2. So therefore, what the attacker does is it can calculate IV1 and IV2 from S0 and S1. So it basically uses this table that we saw. It just falls back to this table and finds out that these are the two possible choices of IV that can take place by using the knowledge of the initial state and the final state. So once you do that, right, you essentially can just check that whether you need to check, right, that whether the IV1 is correct or whether the IV2 is correct. So in order to do that, the adversary looks at the IV netlist. So note that the IV netlist, which is the interrupt logic, it can be either encrypted or it can be not encrypted. Imagine that it is not encrypted. Okay, that means it is kind of unlocked in an unlocked state. So that means that if you feed in these inputs like S0 and the primary inputs, it will give you a corresponding IV value. And now what the adversary will do, that it will just check whether this IV equals the IV1 or it equals the IV2. And if it equals IV1, then it implies that D1 star CA was applied and therefore CK was 0. And if it is not, then it is CK equal to 1. So that trivially leaks the value of CK. So this is a kind of a more elaboration of this attack. So in case one, as I said, that imagine that the interrupt logic is not encrypted. So what you do is you see that whether that you make this transition, and suppose your initial state is S0. So you basically make a guess that the CK equal to 0. So in that case, your D1 star CA successor is as shown over here, or if it is a D1 star CA dual B, then it is another possibility. For both of these cases, you obtain the IV values and you check that whether this IV value matches with your so you obtain the correct IV from the interrupt logic netlist and you check one of them, and that gives you the guarantee that whether the CK is equal to 0 or whether the CK equal to 1. In a more defensive strategy, you may have the interrupt logic which is encrypted, but that also can be circumvented. So what you can do is now you can come up with two possible circuits, say call it as B1 and B2, which essentially are nothing but like your circuits, which essentially stands for it'll produce you the if you take this corresponding circuit, note that this circuit will take the primary inputs and also will give the corresponding outputs. Okay, and now with these two possibilities, this B1 circuit and the B2 circuit, you feed them into a SAT solver, and the idea is that this SAT solver will produce you a key which is either K1 or either K2, and you just match with one of these keys. So this essentially again allows you to perform this attack in a previous, just like as we previously did. Okay, so here are some experimental results of our attack. So this attack was performed on the benchmarks that were published in the original obfuscation paper, and it shows that if you, for example, like in this table, we see that we show here certain thresholds, which stands for the percentage of the state transitions which were locked using CK equal to 1, which is the D1 stars dual CA, or if the CK equal, for the remaining cases it was locked using D1 star CA. In both of them, you will find that that this can be compromised. Okay, and this can essentially leak information. So the question is, right, therefore, I mean, since you can perform these attacks on all these benchmarks, okay, and essentially can de-obfuscate the circuit, then we basically need to kind of understand that essentially this, and we although I show it for a 20-bit key in this illustration, but we also did this attack for larger dimensions of key lengths. So therefore the question is, right, where is the problem? And this brings us to kind of revisit at the cellular automata structure and see that whether we can kind of revisit it and come up with a fix which helps us to protect and provide us obfuscation, at the same time taking the advantage of the nice CA property. So for this, we essentially kind of identify that the reason why essentially it fundamentally breaks is because of the fact that the FSM or the CA based structure is linear. So therefore, right, if you basically this linearity and the fact that you can essentially obtain the next state from the previous state by applying this state transition matrix, means that we essentially need to introduce nonlinearity to the cipher, to the structure of the cellular automata without disturbing its nice cyclic structure. So this can probably help us in thwarting the ORACALL attack. So therefore, this brings us, or this takes back to take a little bit of look at the Boolean functions in general, because at the end of the day, the CA essentially gives me a Boolean map, and look at what we mean by nonlinearity. So we know that a Boolean function which takes an m-bit output and produces a 0-1 output can be captured by an algebraic normal form, which is shown over here, which comprises of AND terms, and the pluses are XORs or exclusive ORs. So together, the XOR and the AND term, you can essentially realize the Boolean function. So this is the canonical form that you can obtain to realize the Boolean functions. The idea or the definition of nonlinearity that we see in cryptographic literature is that if you find out that all the AND terms have got 0 coefficients, then we say that it's an affine function. And in particular, the constant term is also 0, then we have a linear function. However, as cryptographers, we do not like either linear functions or affine functions. So we want to have nonlinearity. So how do you define nonlinearity is quickly illustrated here. So if you take, for example, a simple nonlinear function, which is essentially shown here as x1 or x2, this is a Boolean OR of x1 and x2, then what we do is we take all the possible linear functions like 0, x1, x2, and x1 XOR x2. Note that this doesn't have any of these linear functions, does not have any AND term. And then you consider the truth table of these possible functions, and you start calculating the Hamming distances of the truth tables of the actual function and your approximated linear function. And then you find out these distances shown here as d1 equal to 3. For example, you can see that there are 3 flips. Likewise, this distance has got 1 flip and so on. And then the nonlinearity is nothing but the minimum of these distances. So in this case, we will say that the nonlinearity of this OR gate is 1. So we want that this nonlinearity should be high for the CA structure or the machine that we use for obfuscation. But at the same time, without disturbing the nice structure that we have in the CA. So of course, like you can formulate this in a more interesting manner by seeing what are called as the Waltz transformations, but I will not go into the details of this. But in a broad level, this is the idea of defining nonlinearity of a Boolean function. It is defined as the distance between the function and the set of all possible affine functions. So therefore, the solution that we try to envisage here is we consider that we use cryptographically strong S-box functions. So S-boxes are essentially specific boxes or Boolean functions or nonlinear Boolean functions that are present in cipher constructions. The objective of this is to increase the nonlinearity of your construction. So now what we do here, and they are also reversible, which means they are also bijective in general. Okay. So therefore, what we do now is we modify the state equation in this following fashion. So previously we were taking the state xt and we were applying the state transition as t, but now we modify this by the function alpha t alpha inverse, where alpha is your S-box function. So note that alpha is nonlinear and at the same time alpha is also bijective. Okay. So this essentially uses or is utilized to incorporate nonlinearity, okay, and therefore protect against the leakage of the state encoding that we saw. And so what we basically considered here two possible alternatives. One in which we cascade two popular S boxes along with the existing T, that means the cellular automata T that you have. And in another construction, we modify the rule vector T star with a single S box. Okay, so we modify the cellular automata T to say a matrix called as T star. So therefore, what we essentially claim here is that from the QSM plus 2 pattern, previously, right, I mean, the initial state was leaking trivially. We expect that now that evaluation of the original state will not be so straightforward. So this essentially mitigates the existing vulnerability, and that is our main claim. So how do we choose the S boxes? So in one of our proposals, we also use a cellular automata structure to generate an S box. So this is a paper that we published in FSC in 2018 and shown over here. So the idea of this particular CA-based S box is that we take a Boolean function f and it depends upon the initial input state. So imagine that you have got 4 input bits. So this S box is a 4x4 mapping. That means it takes 4 input bits and produces 4 output bits. So what we do here is we take the input, imagine that you have got a 4-bit vector and you apply this function and you get the first bit. For the next bit, you perform a cyclic rotation of the input and you again apply the same function, obtain the second bit, and so on. So we have seen that using this CS structure, you can get cryptographically strong S boxes or reasonably high nonlinear functions, but at the same time, they are also bijective and they are also invertible. So now if we apply this to this structure, that means imagine that you take suppose a CA-based S box and I call it as beta, and you take another S box from a very popular cipher called as present, and you consider a conjunction of them like alpha and beta. Okay, and remember that alpha and beta are invertible, and therefore the inverse of this can be realized as beta inverse and alpha inverse, and you kind of put the transition T or your CA structure and sandwich it between these two nonlinear structures. And now you essentially have a modified state transition. But the nice property of this is that although you have got now an increased nonlinearity because of these S boxes, but the nice cyclic structure that you had in your D1 star CA is not disturbed. As you can see here, this shows the modified transition of the D1 star CA machines, but it turns out that they essentially have this nice cyclic structure that we originally had. And the reason, right, we have this original structure is also probably can be explained by this simple proof outline. So in the previous case, imagine that if you have in the original CA transition, if you had a cycle length of m, then you will still have a cycle length of m in this transformed transformed construction. Why will you have that? You can easily see this. If I take this alpha beta T beta inverse alpha inverse and I apply it m times successively, then you can kind of like extend this, and you can write alpha beta t, beta inverse, alpha inverse, and then the next structure will be alpha beta t, and so on. So now this alpha inverse and alpha will get cancelled out, beta and beta inverse will get cancelled out, and so on. So gradually you will find that you will have alpha beta t to the power of m, beta inverse, alpha inverse. And since t power of m is I, because you essentially have this cyclic structure, so this will go, and therefore again beta and beta inverse will get cancelled out, and alpha inverse will get cancelled out, and you will be left with the original state x. So you still have a cycle length of m, and this applies to all the cycles that you had in your original state transition graph. So likewise, this is another proposal that we had, where we modified this structure T, which is the rule 102, to a slightly different variant, where it is an XOR of the self right and the right to the right, that is the next right. And if you apply this state transition graph and allow only one single present S box, then also we find out similar kind of patterns where there is a high nonlinearity, but at the same time the cyclic structure as expected is not disturbed. So now, how do you, if we apply this particular structure, and imagine that now your original state encoding was say F1, F2, F3, and F4, and you apply this cascaded S box based cellular automata, and you would like to perform the original Oracle attack that we just now described. So now, if we apply the state transition function, suppose the obtained CA state is now denoted as Z. So Z is the output that we have obtained. So imagine that you have got Z1, Z2, Z3, and Z4. And now if I export Z1, then the question is, if I export Z1 using Z1, because we know that Z1 will follow this equation, can one solve them to obtain the original bits of F? So now one has to solve a nonlinear set of equation and essentially try to kind of obtain back the original bits of F. So it turns out that so these are the two possible constructions. So the previous one is augmented here with, so now in the second construction, we have a present S box with the modified T star. And suppose in that case, we have got W1, W2, W3, and W4, then the problem that the attacker needs to solve is to obtain the F1, F2, F3, F4 from the value of W1, which is the MSB, which is exported. So the nice thing is that now you are not really violating the testability property. You still have the testability property because you are exporting this one bit in the output, but it doesn't become, at least the attacker needs to solve nonlinear set of equation and to obtain the original bit sequences. And in our paper, we have a slightly more elaboration of this to show that the second construction is really kind of a bit stronger, because for any W1 value, we show here that all possible F1, F2, F3, F4 are possible. So note that W1 is a bit, so it can take either 0 value or 1 value. And it turns out that whether it's a 0 or whether it's a 1, all the 2 to the power of 4 possible values of F1, F2, F3, F4 are still possible. So this essentially we summarize here. So we take different types of CA-based S boxes. So this nomenclature, this notation that we use here, 1, 4, 2, stands for the number of cubic terms you have in the construction, the number of quadratic terms, and the number of linear terms. And if you apply the Oracle attack, we find that the Oracle attack fails for all of them. And in particular, for the new construction where we take the T start, which is the modified CA structure, along with the present S box, then there is actually, almost like completely, the Oracle is completely thwarted. That means there is no leakage of the input bits as per our analysis. So this brings me to conclude my talk by this statement that the CA-based FSM obfuscation in its original form, although is promising because of its high testability and not having any requirement of a scan-based DFT, which is not really good for security purposes. But at the same time, right, we saw an attack which is called as ORACALL, which exploits the information which is leaked by the externally observable bit to extract the original state encoding and finally obtain the secret key bits for every transition. On the other hand, we saw that we essentially can potentially augment the original construction, again keeping the nice property of the CA intact, but blending in the required amount of nonlinearity to ensure that our designs essentially do not disturb the testability property, but still is able to thwart the Oracle attack, and like gives promise of a better obfuscation technique. So with this, I would like to say thank you, and if there are any questions, I would be happy to take.
Thank you, sir. Thank you for this talk. And from this audience, if you have any questions.
Yeah, I would like to ask. Okay, Debdeep, nice talk. So excellent talk. So I have a couple of questions, but so first question is you were showing that D1 star CAdual, right?
Yeah.
A property that you can go back to the non-reachable configuration. Okay. So and then you have shown that this is true for a linear case. So
Yeah.
is it applicable for non-linear case?
Well, I mean, what I wanted to show is that, of course, like as we know that there is a lot of prior work, right, to characterize that original D1 star CA, basically, right, in the where the transitions are linear, basically. But now what we want is we want the transitions to be also nonlinear, but still keeping the same structure intact, basically, right? So one solution that I essentially propose here is that if you take the original state transition T, okay, and you have a nonlinear bijective mapping, and you put that across this mapping actually. So you have got, say, let us denote the nonlinear mapping as alpha, okay, and suppose your alpha is bijective, that means it also has an inverse, okay. So if you have got now this sandwiched, if I say sandwiched, like CA, which I call it as, say, alpha T alpha inverse, then this alpha T alpha inverse will have the same cyclic structure as that of your original CA, okay. I mean, it will still have the same nice structures and like the cyclic patterns and so on. The cycle lengths will still not get tampered. It is possible to do that, but at the same time, the transitions will be nonlinear, because now if I take an input state and take an output state, and if I derive the Boolean equations, I will find that there will be AND terms in their algebraic normal forms, which means that now we have a nonlinear transition, but without disturbing the nice CA properties.
So then my next question is that it's a very beautiful thing that, okay, we are increasing, I mean, incorporating nonlinearity, but the original structure remains same or similar. Does it have disadvantage in your case?
I mean, it may have been, I don't know, like it may have certain fallouts, like I don't know, like whether but at least from the cryptographic point of view, I could not find out any nonlinearity, except the fact that it of course increases overhead to your design, right? Because you have got this, like two S boxes sitting at both ends. So definitely that will add on to your, say, like area requirements and power consumptions and so on. But security comes with a cost, right? So we have to live with that.
Okay. Thank you. Thank you. Very nice talk. Thank you.
Hello, sir. This is Kamalika here.
Yeah.
Sir, I have a small query. That is, sir, when you are introducing this many operations over the basic D1 star CA, how much complex it is becoming in terms of its evolution time?
Yeah. So it depends upon how you implement the S boxes. That as I said, that you have got two S boxes, right, at the beginning and at the end. But in the cryptographic literature, right, although of course it will add on to the complexity because there will be more gates that will get into it. But I have not done that in person. But I believe that there are many like techniques that people have developed for implementing the S boxes efficiently, actually. So those can be now brought in along with your CS structure and do the optimization of the overall structure, actually. So like if you take maybe like if you allow, say, a CAT tool, for example, like a synthesis tool, and you feed in the entire function and you tell it to optimize, it will be the original CA. Of course, I anticipate that it will increase, right, the cost, but I still do not see that the cost will be too humongous, to rule out a reasonable application.
I was asking this because recently we were trying to introduce non-linearity in a CA-based pseudo-random number generator using the popular S boxes. But while we run it, it became very heavy. Like it was taking too much time in terms of computation.
Yeah. So it depends upon what kind of S boxes you are using. So if you see, I've used the S box for present, which is a lightweight cipher actually. Okay. So if you use an 8x8 S box and if you use a 4x4 S box, there's a huge difference in terms of its impact. Okay. So if you have taken a small S box like a 4x4 S box, and if you choose this kind of S boxes like those are present, and there are other kind of ciphers like Kechak and so on. I mean, not Kechak actually, but like LED and so on, right? Which follows in the category of lightweight block ciphers. Then there are very interesting proposals actually, where you can do with very, I would say, minimalistic overheads actually. So don't use an 8x8 S box because the cost will increase exponentially. But at the same time, if you require to use an 8x8 S box, then there are also very compact descriptions of AES S box also, like which uses this nice isomorphism of fields. And like if you take an 8x8 S box, which has got, say, which can be represented in a GF2⁸ field, you can apply isomorphism to write down in a very simplistic structure. You can make GF2⁸ use the fact that it is isomorphic to GF2 and you can realize it only using small 2 square elements. And interesting point is that in GF2, you have you can realize the S box in a very compact fashion. Okay, so you have to use those literature and use an optimized design of the S box. But my first level suggestion is to use the 4x4 S boxes. They are easy and they are efficient.
Thank you so much.
Okay.
Sir, I have a small query.
Sure.
So what means the cycle length? What is the cycle length that will be proved efficient to implement this S box means in your logic? Or
if I understand your question, you are saying that which kind of cycle lengths are useful.
Yeah, means
Yeah,
there is any optimal relations with the S box and all this.
So first of all, right? I mean, what I just changed is only I didn't change the D1*CA actually. That is a well-established theory actually. Okay, so I just wanted to say that if you want to use the CA structures for security, for cryptography or obfuscation, then you have to incorporate non-linearity. Okay, so the contribution that I was trying to speak over here was how to blend non-linearity without disturbing the original nice cyclic structure. So the cycle lengths are, I would say, dictated by your CA property actually. Okay, so I mean, the reason why probably, I mean, like maybe Professor Das can better talk about that actually. I think the reason why, like the CA structure is useful, the D1*CA, is because of its nice testability properties actually. And essentially, and maybe there are many other such applications of the original CA. But the only point is, I mean, people probably have tried to apply CA for cryptography, but one of the major deterrents has been this fact that they are not linear. I mean, they are not non-linear. Okay, and I think therefore if you want to apply it for security, then this is a direction of research.
Okay, thank you, sir. Any other questions? Thank you, sir, for this nice talk and also for attend all these queries.
Thank you.